All right, let's talk about something pretty wild. The quest to teach machines how to speak. I mean, really speak, just like you and me. We've gone from those classic robotic voices to something, well, something that's almost impossible to tell from the real thing.
You know, for as long as we've had computers, this has been one of the holy grails of AI, right? Taking plain old text and turning it into speech that sounds genuinely human. And it all boils down to this one deceptively simple question.
So yeah, how do you do it? How do you get a machine to understand not just the words, but the tone, the rhythm, the humanness of speech? To figure that out, we gotta look at how the pioneers first tried to crack this nut.
Okay, so before deep learning came along and just flipped the whole table, we were kind of stuck in this uncanny valley of voice. You know what I mean? The voices sounded almost right, but there was always something just a little bit creepy or off about them. And that's because, back then, there were really only two ways to do it, and both had some pretty big problems. So on one side, you have this method called concatenative speech. The best way to think about it is like making a ransom note out of magazine clippings, but with sound. You'd have this massive library of pre-recorded audio snippets, and the computer would stitch them together. It could sound pretty good sometimes, but man, it was so inflexible. Then, on the other side, you had the parametric approach. This was more like a puppet, a mathematical model of a voice that you could control. It was way more flexible, but it's the reason we all have that classic monotone robot voice in our heads. Not exactly natural.
And then, deep learning happened. And look, this wasn't just a small step forward, this was a complete paradigm shift. It wasn't about improving the old ways, it was about throwing them out and starting with a totally new playbook.
See, instead of trying to reuse old sounds or just model a voice, deep learning models learned to generate the audio waveform itself right from the ground up. I'm talking literally creating the sound one tiny digital sample at a time. And the result? Whoa. It was a quantum leap in how natural these voices sounded.
All right, so the first real shot heard around the world in this new era came from Google's DeepMind. They unveiled a model that basically set the blueprint for everything that came after. It was called WaveNet.
So how does WaveNet work? Well, the core idea is actually pretty elegant. The network looks at a sequence of audio samples, the sound that's already been generated, and its entire job is to predict the very next sample in that sequence. It's almost exactly like how a text AI predicts the next word in a sentence, except this is happening thousands upon thousands of times every second. Pretty wild.
The secret sauce here is something called a causal convolution. It's a fancy term for a simple rule. You can only use the past to predict the present. The network is strictly forbidden from peeking into the future of the audio stream. This is absolutely critical because that's how we speak, right? This forces the model to generate sound in a natural, moment-to-moment way.
Okay, but this one sample at a time thing creates a pretty big headache. For speech to sound right, you need context. You need a long memory. The sound you make now depends on the word you started a second ago. Well, the brute force way would be to stack a ton of layers, but that would make the model gigantic and unbelievably slow to run.
And this is where the engineers got really clever. They used something called dilated convolutions. Instead of having each layer look at the sample right next to it, they programmed the layers to skip. So one layer might look at every second sample, the next looks at every fourth, and so on. It's like having telescopic vision into the past. This lets the network have a huge memory of the audio history without needing a crazy number of layers. Super efficient, super smart.
So, with all this complex tech, how do you actually measure if a voice sounds good? It's pretty low tech, actually. They use what's called a mean opinion score, or MOS. Basically, you get a bunch of people, play them the audio, and ask them to rate how natural it sounds on a scale of 1 to 5. A 5 is basically perfect, indistinguishable from a human. And when they ran the numbers, the results were a huge deal. The old school methods, the audio collage and the robot puppet, they were hovering around a 3.7 or 3.8. Good, but not great. WaveNet, it came in at a 4.21. That doesn't just beat the old methods, it blows them out of the water. It closed over half the gap to perfect human speech in one fell swoop. A total game changer.
But here's the thing about breakthroughs like WaveNet. They aren't the end of the story. They're the starting gun. Suddenly, everybody saw what was possible and the race was on. Labs all over the world started jumping in, each trying to build on this new foundation. Things started moving fast. One of the first big players to follow was Takatron, also from Google. Its big idea was about elegance and simplicity. Instead of a bunch of separate, clunky steps, Takatron was end-to-end. You feed it raw text at one end, and out the other comes a spectrogram.
which is basically a blueprint for sound. It streamlined the whole process. And it worked pretty well. It scored a 3.82 on the MOS scale. Now, that's really impressive for a brand new end-to-end approach. But it was still just a little bit behind the very best of the old-school audio collage systems. So the gap was closing, but it wasn't quite there yet. Meanwhile, over at Baidu's AI Lab, they came at the problem from a totally different angle, with a system called Deep Voice. Instead of building one massive do-it-all model, they built a team of specialists. It was a system of 5 smaller neural networks, where each one had a very specific job, like figuring out pronunciation or timing. It was a divide-and-conquer strategy.
And they iterated on that idea super quickly with Deep Voice 2. This time, they tackled an even bigger challenge. Could they build a single model that could learn to speak in hundreds of different voices? And not just that, but could it learn a new voice from just a tiny snippet of audio? The goal was now multi-speaker voice cloning.
And this is where things get really interesting. People started to mix and match. They realized, hey, what if we take this smart front end of Tachytron, the part that turns text into a spectrogram, and then plug that into the amazing audio generation back end of WaveNet? And when they did that, wow, the quality shot up to a 4.17. It was the best of both worlds, a true hybrid.
But there was still that one big problem we talked about: speed. Generating audio one sample at a time is powerful, but it's slow. So to fix this, they came up with Parallel WaveNet. The idea is just genius. You take your big, slow, but super high-quality WaveNet model, that's the teacher, and you use it to train a brand new, much smaller, faster model, the student. The student learns to mimic the teacher's output, but it can do it in parallel, making it thousands of times faster.
So you can see where this is all going, right? All these amazing ideas, the end-to-end architecture, the high-fidelity audio generation, the speed improvements, they were all about to come together. This innovation explosion led to a model that combined the best parts of everything and pushed the quality into territory that was honestly science fiction just a few years earlier.
And that model was Tachytron 2. It's the ultimate combination. It uses the smart, efficient text-to-spectrogram part from the first Tachytron. Then, it feeds that sound blueprint into a super-powered WaveNet vocoder, which handles the final step of creating the actual high-quality audio. It's the dream team.
So, the big question: what was the score? Tachytron 2 clocked in with a mean opinion score of 4.53. Now, to put that in perspective, actual, real, professionally recorded human speech scores around a 4.55. We're talking about a voice that is so good, it is statistically almost impossible for the average person to tell that it's not a real human speaking. Just let that sink in.
And that leaves us with a pretty heavy question, doesn't it? We've basically done it. We've reached the point where we can create perfect copies of human voices. Now that the technical challenge is solved, we have a whole new set of challenges. How are we going to use this power? And when any voice can be faked perfectly, how do we know what or who to believe anymore?